Hey, AP Chemsters, this is Mrs. Vanderwall with another edition of the Blank Wall series. Today we're going to do 13.4, the integrated rate law, and I asked you to get out your equation sheets right now. So why don't you pause this and look for your equation sheets. So hopefully you found this particular equation sheet. If you scroll down to the bottom, let me get there, and you're going to notice that down here it says kinetics. This is the area right here that we are very interested in, and I'm going to have you write on that as we proceed through this next section here. So let's go back to our notes. And before we actually begin, let me just kind of remind you of a couple things. We talked about a flipped classroom. If you ever need to pause because either I'm going too fast or you're writing slow or whatever, you just are tired of hearing my voice, go ahead and pause, catch up, and then you can always, scroll back and continue on where you need to go. Make that as a general rule. Also, make sure you have a calculator and make sure you are calculating with every step that I am so you get familiar with how to go about doing this work. So what is this section about? It's the integrated rate law. If you recall back in section 13.3, we were talking about the general rate law where we are always comparing the concentration of one of the reactants and the rate itself. No place in that did we talk about the time factor. How much time did this all take? And in chemistry, time is a very important consideration. So how do I now go from concentration to time? Using a lot of calculus, and don't worry, you are not responsible for its derivation, just know how to use the equation. But using calculus, we can go from the rate law to the integrated rate law. Now we're starting off with a first order. So notice everything we're doing in this whole section here is going to be a first order. And that's right here. So what was a first order from last section? That is when we said if the concentration of A redoubled, then the rate will double. Okay, so what is the rate law for that? Well, here it is. This is your calculus derived equation. So let's kind of get a couple things straight here. This natural log of A in the brackets is the concentration of A at any time T, whatever T you want. So if T is down here, all right, what is the concentration? That's going to be this value right here. Negative K. K is the rate law constant, just like the one up here. These are going to be the same numbers. T is time, and natural log of A naught. What does this naught do for you? This naught is the initial concentration. How much did you actually start with? So on the graph, that would be this value right here. All right, so where were we? I had to pause that for a minute. So we have the initial reactant. Oh, that's right. That's your A naught here. And again, when we look at this relationship, this is your y equals mx plus b, just like we have down here. So what does that mean about our slope? Well, if I look at the y equals mx plus b, your m is your k value. So that, I'm sorry, your negative k value. So that's the slope of the line. And so that's a very, very helpful tool to help us calculate. Now I want to show you one more thing. Do you see this over here? What they've done is that they've rearranged how they wrote this. So if you know anything about your rules of logs, if you were to go ahead and subtract ln of A from both sides of A naught, I'm sorry, okay, subtract that from both sides, you'll have ln of the A, this is really messy, sorry, that's the A, minus the natural log of A naught, right? I'll just do it this way. So in the rule of logs, what do you do with that? You divide it. So this term is now equal to natural log of A over the natural log of A naught. But wait a minute, this is flipped. A naught's on top. Why is it flipped? Because they got rid of the negative sign. And this is going to be really important when we talk about half-lives, which is, I think, on the next page or so. So keep this in mind. When you subtract A naught from both sides, you end up dividing it. And then with the negative gone, you flip it. So natural log of A naught over natural log of A is positive KT. Now, this doesn't help us in the y equals mx plus b form, but it'll help us understand half-lives later on. So let's go ahead and look at the next, or look at the first problem here, problem number, whatever that is. So let's read problem number 12. Oops. what's this going on here? It says a decomposition is a first order reaction. Okay, so that's a really important clue here. So because it is first order, we know we can use that equation from before. And it has a rate constant. That's our K value right here. The reaction is carried out at the same temperature. Ooh, foreshadowing of things to come. We're going to find out the temperature does relate to this. And has initial concentration. That's our A naught right here. We're asking for, well, what is the concentration at a certain time? In this case, 865. So we have all the points that we need. All right, so because it's first order, we can say this. Natural log of A is equal to negative KT plus natural log of A naught. So now pause this for a second and plug in your values and see how you do. All right, hopefully you got it. Let's plug in the values here. So our constant is 2.9 times 10 to the negative fourth, but notice I put the negative out in front. Don't lose that negative, very important. We have 865 seconds. And what can we do with these seconds? Notice that we can cancel them out. And then we have the natural log of our initial amount. There's our initial amount of 0.0225 molar. So what's next? Well, I combined all the terms. And if you were doing your math, I sure hope that you got this value here is negative 0.251, and this value here is negative 3.79. Add those together, you should get this value. And now, how do you get rid of the natural log? If you are just solving for this value right here, how do you get that by itself? Well, how do you get rid of the natural log? If you remember again, your rule, you have to take the natural log. So take the E value. So what's E of negative 4.045? That's your initial molarity. So you take this number, that becomes your exponent of E, and that's your new molarity. All right, let's talk about half-lives, if you will. Turn the page. Okay, so this is the half-life, again, of a first-order reaction. First order means if you double the concentration, you double the rate. So what is a half-life? Oh, please, please commit this definition to memory. The half-life of a reaction is equal to the time. So the half-life is a time quantity required for the reactant to reach half its original concentration. That's why they call it half-life. Pretty catchy, don't you think? So here they're saying that that initial value divided by 2 is the half-life amount. So the time it took is the half-life of the reaction. So do you remember this equation from above from the prior page when I made a big deal about why this is A naught over A and the negative dropped out? All right, so we're just going to substitute some numbers in here. Notice that the 2 is in the denominator of the denominator, which makes a 2 on the top. And so here we have the actual equation. And go back to your equation sheet. Do you see that third reaction, or the third equation? I'm sorry, will you please write this? This is the half-life of a first order. Put that on your equation sheet right now. First order half-life reaction, or equation again. So let's check this out. Here we have, what I would like you to do is actually copy down this chart I just put up there for you. And this chart we're going to refer to throughout some of these problems here, okay? So a half-life is a whole number. 1 half-life, 2 half-life, 3 half-life. Starts off with 0. So before the reaction has begun, 0 half-lives have passed. Here's your real time, like how many seconds, how many minutes, how many hours we have. And here's our concentration. At the initial onset of the reaction, you're going to always have the original amount, 100% of your reactant. After 1 half-life, you're going to have 50%. After 2 half-lives, you have 25, and so on. And this picture over here really shows you that. So if you look, you will see that here I have the original amount, and they're using a 1 instead of 100%. Hopefully that makes sense. And you can see all the little dots here. And notice 1 half-life later, in this case is 100 seconds. How much do we have left? We have only half the concentration. We've lost half our reactants. After 200 seconds, or 2 half-lives, we have 25%. After 3 half-lives, we have 12.5. So those numbers would be the half-life. So in this case, 1 half-life would be 100 seconds. 2 half-life laters would be 200 seconds, and so on, according to this graph. So let's check out problem number 13 and see how this all works. All right, so problem number 13 says a decomposition of N2O5 in the gas phase was this probably the student's reaction at constant temperature. So the very important thing here is the reaction is known to be first order. So that's really important. Now, if you notice, there's a little bit of a change here, isn't there? Please insert this word integrated in your notes. Very important that you do that. I left it out. I apologize. So use the integrated rate equation and determine K. So what's our integrated rate equation? It's this one again. If I were you, I'd write small. I don't think I gave you enough room. So we're going to use that. And so what's the integrated rate equation? Let's plug in some numbers. Now, what I would do if I were you is pick any of these over here. Okay, you're allowed, because we're going to get the same constant no matter what. That's what we're trying to do, is solve for K. Now, something that you ought to know, though, is that this number is what? Times 0. What did we say times 0 was? That is our initial amount. This is our A naught. So reserve this for your A naught, but you're allowed to use any one of these to solve for K. So why don't you pause this, pick one, and solve for K. See how you do. Okay, let's see what you did. I picked the last one for the heck of it. Why not? All right, so I'm using these numbers. So notice that here is my concentration and here's my time. Then what did I do? Well, I went ahead and solved for the values. And so the natural log of 0.00625 is this. Here, we all should have this value. And so then I added 2.303 to both sides. And then I solve for K. There it is. Notice your two negatives cancel out. Notice that the 400 seconds, when I divided it, seconds is now the denominator. So that's my K value. And does this make sense? The answer should be yes. Why? Because look at the units. Remember, that was our consistent unit for any first order constant. Now, we're supposed to calculate the N2O5 at 125. We can do this now because we know what K is. Oops, I went down a little too far. All right, so same equation that we're going to use. It is first order, so we're allowed to use integrated. Notice that time is a factor here. That's why I need to use the integrated rate law, because I have a time factor and I'm working with concentration. And so, okay, I'm going to be more specific now and work with the N2O5. And now that I have the K value, I can plug everything in. Here's my K from problem A. Here's my 125 seconds, and this is my natural log of 0.100. So let's go ahead and do the math, multiply these two together. Oh, but if I were to do that, what happens to seconds? Seconds cancels out. That's a good deal. So I'm going to plug this number in. And so when I multiply these two numbers together, I get negative 0.866. I'm running out of room here. I'll go over here. So that's your natural log is negative 3.169. How do I solve for N2O5? Remember, you have to take that E value. Remember that? So I have the E value. Go ahead right now. Pause this if you need to and plug this into your calculator. Make sure you're doing this right. See what you get. This is what I got. Hopefully that's what you got. Okay.